This video will cover material that we did in class on Lesson 28 in Math 378. It concerns a problem about wear on lenses. And down here we have our data. In the left-hand column, which is our predictor, we have the wear, and in the right hand we have the treatment, and there are 4 different treatments. And we want to see if there's a difference in the average wear between the different treatments, which leads us to ANOVA. First thing we're asked to do is enter the data. A common mistake for people is not to put it in the regression format or the multi-factor format, instead to put it in the one-way layout, and I'll show you what that looks like. This is a common way that people put it in. Problem with this data is it's treating each treatment as a vector, and we need to treat the entire response variable wear as one column and the treatments as another. If you enter the data in the one-way layout, easiest way to uncover it or to recover it is to use the stack command. And it'll give you the data back. Starting with the data, first thing we would like to do is summarize it. So I'll summarize my data. Nice tabular format. When you look at this, I have a summary for each treatment as well as the overall. A couple things to look at. We can see the means, of course, are not all equal. They're sample means. But it appears treatment B has a little higher mean wear. Treatment D is a little bit lower. We see values around 12 for A and C. D's at 11, B's at 14. Standard D's, we have assumption of constant variance. Standard D's, 2 at the high end, 1.3 at the low end. Quick rule of thumb is if take the ratio of the largest one to the smallest. In this case, 2.1 to 1.3. That ratio is less than 2. Constant variance, probably not a bad assumption. We also like to summarize the data in a visual manner, so I'll go ahead and plot it. What's nice about the plot command, if I use wear as my y variable and treatment as my x, since treatment is a factor, R is going to know on the x-axis to put it as 4 different values, A, B, and C. Here we can see the box plots. We can see the means plotted. We can see B being much higher at the 14. There might be some skewness in B. A, which had a standard deviation of 1.4, actually has an interquartile range that's a little less. We have one point that's sort of an outlier and an extreme. And so we'll have to check our assumptions after we do ANOVA. But that's the nice thing about the visual summary, is we can see those types of features. Go ahead now and do our analysis of variance, ANOVA. So I've saved it in a variable. Let's do a summary of it. All right, a couple things to notice here. Treatments, degrees of freedom, 3. Because we had 4 treatments, we lose 1 degree of freedom to estimating the overall mean. Residuals, within each of the treatments we had 7 data points, but in each of those we're estimating 1 mean, so we have 6 degrees of freedom in each one, and there's 4 of them. 6 times 4 is 24. Sum of squares, this is the difference between our treatment means and our mean, overall mean squared. Add those all up, and then residuals are within treatment, difference between my observed values and my treatment mean, those differences squared and added up. To divide by the degree of freedom, it gives me an estimate of the variance between treatments, 12.25. In the variance between unexplained or error, 2.512. That ratio is about 5, and when I account for the fact that there's randomness, it gives me a p-value 0.00869. Remember, my null hypothesis is where all the means were equal, so based on this data, I reject that in favor of the alternatives. It said that at least one of the mean wearers in this data set of plastic for one of the treatments is different than the others. All right, assumptions. We had assumptions of normality and also of constant variance. One command we can use is just to plot on the model. First plot I get shows fitted values versus residuals. We're looking for a constant band. We see a little bit high for one of them, but overall not too bad, which we expected. And then our quantile plot, we see some flatness sort of towards the edges. So it's not quite normal, but not too bad. And I won't look at the others. You can also, if you wanted to plot them by hand, not by hand, by your own commands. Here's the commands as well. And we talked about the QQ norm plot in class. And this one's the constant variance. All right. So that's it for the ANOVA. Now what we'd like to do is do a confidence interval for the mean of A, just to practice. Going back up, I can look at my data, and I can see the mean for A, its standard dev. If I wanted to generate a confidence interval, I could take the mean, 11.986, plus or minus so many standard devs, where the standard dev is 1.4, divided by the square root of 7. The standard devs then will come from a t-distribution with 6 degrees of freedom. Or I could actually use the estimate of 2.512 as an estimate of sigma squared, so I could take its square root. The advantage of using it is it has 24 degrees of freedom, so the t-distribution might not be as fat. So I'm going to go ahead and do a 95% confidence interval. So first thing I'm going to do is capture the mean in a variable. So what I'm using here is a tapply command. So I'm calculating the mean of each of the A, B, C, and then I'm using the 1 to just get A. I'll save that in the variable I call mean A. And then to calculate the confidence interval, I'm going to add and subtract the appropriate number of standard devs. So here I took my confidence interval is 0.95, so I had 2.5% of each tail, 24 degrees of freedom. Took the square root of 2.52 over 7. 7 was the data points, the n in that sample. And it looks like my confidence interval goes from 10.75 to 13.22. I'm going to unstack my data to run it through t-test. So prob 13.30 un is my unstacked data. I want to see that. I can type the command in so we can see. There it is. And then I'm going to run t-test on column A. And here you can see the confidence interval. It's just a little bit wider. 10.7 to 13.3, whereas before we went from 10.75 to 13.2. And that's the lesson that we did in class on ANOVA and confidence intervals.